Hello and welcome to the limit group worksheet worked out solutions. So we'll first take a look at number 5. This is a really good continuity to point problem. So from Calc AB, you probably remember that there's 3 aspects to determining continuity, which is that at the point x equals a, that 1 f of a is defined, and then 2, the limit as x approaches a of f of x exists. So in other words, from left and right they have to equal. So within the piecewise function, these 2 functions have to be equal to each other at x equals to -7 for that example. And then lastly, the limit as x approaches a of f of x has to equal f of a, which makes sense if you look at it graphically. So for this example, f of -7 is given right here at -4/7. So the first criteria is met. And if we go ahead and find the limit, we'll first do the left side limit, or this function from the piecewise. So it will be the limit as x approaches -7 from the left, f of x is equal to the limit x approaches -7, x plus 7. And this may be hard to visualize numerically, but if you graph the natural log of x plus 7, it looks something like this. So from the left, it does not exist. From the right, it equals -infinity, but the left doesn't exist. So therefore, this does not exist, which I'll abbreviate as dn. And since this doesn't exist, then the limit itself as x approaches -infinity of f of x also doesn't exist. So since that criteria is not met, then the function is discontinuous at the point. So we can say since the limit as x approaches -7 of f of x is discontinuous, or does not exist, then f of x is discontinuous at x equals -7. Alright. So that problem may have been probably reviewed for you guys, but I can assure you that the next problem you've almost definitely forgotten. Personally, I forgot almost entirely how to do it. And of course, talking about number 6, which is asking us to convert this integral, so the integral from 0 to 10 of 10x times secant of 2x over 87x squared plus 2x dx. So it wants us to convert this to limit notation. So if you have forgotten what limit notation is, it's actually the limit definition of an integral, which is in the form of the limit as n approaches infinity of the summation from I equals 1 to n of f of xi delta x. So that probably looks somewhat familiar to you guys, but in case you've forgotten, delta x is just the change over the interval, which can be denoted as b minus a over n. And then xi is a plus I delta x. So once you know these formulas, it's pretty easy to rewrite it, but it's just the knowledge of having this is what makes it difficult. So delta x in this example is 10 minus 0 over n, so that's just 10 over n. And then xi is just a plus I times delta x, which a is 0, so it will just be 10i over n. So with this knowledge in hand, we can just rewrite it as the limit as n approaches infinity, the summation from n equals 1 of f of xi. So we just replace all the x's with this, basically. So it'll be times delta x, which is 10 over this would be a monster to actually compute, but that is in the correct format. Alright. Alright. Number 10. This is going to be a throwback. So let's just look at this problem and see how we might approach it. Alright, so just looking at the problem, you can see that if if we do direct substitution, it will be cosecant of 9 over 0, which is cosecant of an undefined term. And since it's a two-sided limit, we actually can't do any one-sided manipulation. So we don't really know what to do. But if you remember from Calc AB, this format will probably look very familiar to you. So if there's any trig function times another x function, or a simple polynomial like x to the fourth, then you usually have to use the squeeze theorem. If you've forgotten what that is, then I'll do a quick review. So squeeze theorem. So the reason why these appear in trig functions a lot is because, well, let's say sine, so -1, or sine is between -1 and 1, or sine of x, sorry. And so it's really easy to manipulate this to get other trig functions as well, so that you can use squeeze theorem. And so I'll just go through this. So if we start out with this, and then we take the reciprocal of everything, so it would be 1 over -1. Then we have cosecant of theta, right there. And I'm sorry, I should actually rewrite this as -1. It's in between sine of the angle theta that's used in the function. It's in between -1 and 1. So from here we can just cube everything, because that's perfectly legal, because as long as they're equivalent, that's fine. So it would be -1 cubed to cosecant over x cubed between 1 cubed. Alright, and so now that that's done, we can just multiply everything by this polynomial function that's there. So it will be negative x to the fourth, so in between cosecant over x, or cubed, or sorry, cubed times x to the fourth, which is in between x to the fourth. And it's in this format because these limits are very easy to analyze. So basically, the squeeze theorem states that if a function is in between two functions you can analyze and find the limits of them, if these two are both equal, then this must also equal the limit. So let me explain. So we can say the limit as x approaches 0, negative x to the fourth is equal to 0, correct? And then the limit as x approaches 0 of regular x to the fourth is also equal to 0. Alright, so then we can say therefore, by squeeze theorem, or therefore since, and use this sentence. Since this is true, so basically it's saying that since this this function is sandwiched in between these two functions that we know the limit of, so we're saying since it's between this, and because of that, so and the limit as x approaches 0 is equal to 0, which is equal to the limit as x approaches 0 of x to the fourth. And we can say then this must also equal 0 by squeeze theorem. So really this is just manipulating trig functions, or mainly trig functions. Don't quote me on saying it's only trig functions, so it's going to be applied to other things as well. But it's most commonly seen in this format where you can't do anything numerically, so we have to use squeeze theorem. Alright, now we'll be looking at the very last problem, which I think it can be done in multiple ways, so it's a really interesting one. So number 15. Alright, so just looking at some methods we can do, I see this square root, And I'm tempted to just automatically multiply by the conjugate because we were taught to do that in Calc AB when we first learned limits. That was one of the methods we were taught. But that actually doesn't seem like the best method here because if you just remember your rules for end behavior, then you remember that we can multiply by a fancy one. And fancy ones, they can at times completely break math, and here I guess is one of the instances of that. So as you can see here, these cancel out. So we're basically just dividing the top and the bottom by x squared. So if we do that, then we get this. And always remember to keep the limit. So don't drop the limit. You have to keep writing it no matter what happens. I know it's annoying, but it's a very common mistake that students make because this function alone is not equal to analyzing the limit as x approaches infinity. So we just have to remember to keep that limit. X over x to the fourth minus 4 over x to the fourth plus 7 over x squared. And it's x to the fourth inside of the square root. Sorry, this is an extent. But it's inside of the square root because if you remember, you have to make it the square so that it's inside the square root and it's equivalent. And that's over x squared over x squared plus 2x over x squared minus 24 over x squared. And then that's equal to the limit. Do not drop the limit of and then if you remember, anything over x as it goes to infinity will equal 0. So it will equal 0 plus 0 over 1, which equals 0. So that's one method. The other method is L'Hopital's. So thus far we haven't covered L'Hopital's, but I think you guys know that you have to follow a very specific notation when analyzing L'Hopital's and prove that it actually applies in the scenario. So basically with L'Hopital's, I'm going to start this. Just never say 0 over 0 or infinity over infinity. Because that is in indeterminate form and it can only be expressed as a limit. So that's why you have to do it as a limit. The limit as x goes to infinity. Oh, sorry. What am I doing? I'm going to reverse your note card on that. Reverse your note card. Gotta just take it back a notch right now. Is equal to infinity, and then likewise the bottom is equal to infinity. And that is an indeterminate form, and so therefore L'Hopital's applies. So then we can say apply L'Hopital's because we just proved that it's in an indeterminate form here. Apply L'Hopital's, and then you'll get, remember derivatives, 1 over 2 square root x minus 4 over 2x plus 2. And it's not good to have a fraction over fraction. Oh, reverse your note card again, I made a mistake. See? Remember to not drop the limit, guys. So here it would actually be the limit as x approaches infinity of 1 over 2 root x minus 4 times 2x plus 2. And then since these are all x values and then they're in the denominator, it'll go to 0, so then the limit equals 0. So we got the same thing from two different approaches.